Hey kids, time to do flux. Sounds like a cool word, doesn't it? Flux. All right, so with flux, the surface integrals, remember we were able to think about a almost like a 4D, in 4 dimensions, right? On this 3D surface, what else could be going around it from its surface, right? Maybe it was a temperature function, and we think about this as a hemisphere of the Earth or something like that. Or we have a shape whose density, right? This is a solid whose density varies over the shape. Well, I do want you to kind of think of a vector field now. And where the vector field is swirling all around this. And flux is going to give us a measure of the degree to which the vector field crosses through this surface. Now, there's some conditions that I'll talk about in a minute, but first I kind of just want to show you a visual of this surface. Look at this here. Here's the surface. So the first thing that you're going to see is like a vector field. The vector field is going to be in blue. As the vector field goes around this, right, here's my surface, there's the vector field swirling all the way around it. And then next you're going to see the normals. Do you see that? These green arrows are all the normals coming out of that surface. So one of the conditions are that we have a closed surface. So a hemisphere is closed, right? If we close off the bottom, a closed surface, and we call it and I'll define this a little bit in further slides. Orientable, if I can say that right, means that I can draw normals coming out from this. I call this an outward flux. I can then also measure inward flux if I make all the normals go inside. But we primarily talk about coming out of the surface. So think about all these normals coming out of the surface, and then a blue vector field swirling around it, right? Kind of cool, right? So we want to know about that vector field as that vector field is going, because it's going all, that blue is going all the way, it's going through that surface, right? So we want to know to the degree to which it crosses through. How much, and if you think of the vector field as a fluid, that's why I put fluid in quotes, how much of it is leaving this surface as the fluid flows along the vector field. And I have leaving highlighted because leaving, think of as coming out of the surface and entering, going in. And I said most times when we're talking about flux, we're talking about coming out. So just like we're line integrals, the orientation of the curve could change the answer. The orientation of the surface will change the sign of the answer. A surface is closed, right? If we have a curve that is the boundary of some solid, think of easy ones to think about are spheres, hemispheres. We call it orientable if it has two sides. The surface has two sides where I can think about a tangent plane at every point. And that tangent plane has two unit vectors, one coming directly out and one going directly in. So the whole surface with each one of these points and each one of them having a tangent plane will have two sets of normal vectors. Like that picture, the set of all the normal vectors coming out, the set of all the normal vectors going in. The set we choose to work with gives the surface the orientation. And coming out, a closed surface has a positive orientation if we choose the set of unit vectors that point out, and negative if we choose the set of unit vectors that point inward. So here's a picture from your book, right? So here is part of a surface. And as you can see, here is a point on the surface, and there's the normal vector coming out. We call that positive n, negative n going directly back into the surface. So here is a surface with a whole bunch of different points where we have chosen the set of normal vectors that all come out. Here is a surface that is orientable that we chose all the unit vectors that are going in. A Mobius strip is a good example of a non-orientable surface because as you travel around, right, as you travel around the surface, the normal vector that was pointing out becomes one that is pointing in. Okay, so this is non-orientable. We are going to be dealing with orientable surfaces. So we want to find the volume of the fluid flowing through this piece of a surface area. So we're going to I want you to think of this little teeny surface, right, on my larger, like maybe hemisphere or something like that, right? So this is like my tangent plane. And there's a point on the surface. Here is the normal, right? There's the normal. Here is my force field, right? My force field coming around. Now, think about this. So my force field is determined, right, is defined by X, Y, and Z. Look at what happens if I dot these two vectors. The force field vector with the normal here. If I dot that, think about what happens when your dot product is 0. What's true when your dot product is 0? The two vectors would be parallel, right? This would be a dot product that is, and then the force field is tangential to the surface, right? If the dot product is not 0, then think about what this dot product tells you. This dot product tells you how parallel these two vectors are. In other words, how much your force field is in the direction of the normal. And if I do that all over the place, right, here's my little mini version of what I just drew you, right? There's the normal coming out of there. Here's the force field there coming out there as it passes through the surface. If the dot product F dot N was 0, then I would be tangential. The force field would be the vector field would be tangential to the surface. There would be no crossing of that surface boundary. But if F dot N is not 0, then the value of the dot product tells you the proportion of parallelness of how much the vector field is in the direction, the proportion of the field that is in the normal direction. And of course, if I can do that at one point, I can do that at a bunch of points, and I will sum them all up, right? If I add them all up, I have the flux of my vector field through the surface, right? Sum up all of those proportions. Oops, sorry. But remember, this is often, right, that ds is often annoying to integrate. We need to try to, right, we can deal with dot products here, but this ds is annoying. So I'm going to give you two formulas for flux that transform this dx and make our integrals easier, relatively, to integrate. So here's example 1. Here is, I want you to compute the flux through this surface, and I've colored red. It kind of looks like a rocket, doesn't it? Red, the bounded surface. So I'm bounding the paraboloid between 0 and 4, right? So z equals 4, z equals 0, z equals 4. So it is closed, right? It is orientable, right? Because any point that I pick and draw a normal, any point I pick along this, the normal will be coming out. So step 1, remember, I need to compute F dot N. So the first thing I have to do is get my normal. I have my F. Here's my F, X, Y, Z. Here's my vector field. I now need to find the normal. So what I'm going to do is I'm going to set z equal to 0, rename it little f, and determine the gradient, right? That's how we get the normal. So gradient of f, and then I want the unit normal. Say unit normal. And that's going to be my n. Then I'm going to get the dot product of my vector field with my normal, my unit normal. Then I'm going to transform ds into dA. Remember this from before, right? Delta surface area. We did this proof with the cross product of the little partials. And then we're going to integrate. So this is first way. First flux formula. I suggest for your homework, I gave you 4 problems. I suggest that for homework number 17 and 19, you use this formula. All right, so let's go. So step 1, I needed to set z equal to 0 and rename it little f. Find the gradient of f, partial x, partial y, partial z. Normalize it, right? Square root of partial squared. Step 2, dot product. Looks kind of hairy, but notice something nice happened, right? I'm just multiplying. We're doing the dot product here. I'm just kind of factoring this out. Dot product there, here, and z all over this. Now look at transform your ds into dA, which is just the square root of these partials. Squared plus 1. And wasn't that nice? Notice what happens here. What is 2x squared plus 2y squared? Oh, snap. There's some really nice algebra happening here. Those go away. Woohoo! Now notice I colored z blue. What do you think you're going to have to do with that? Yeah. All right, so now I'm down to a place where I've cleaned this up a bit. This seems a bit more manageable, but remember what our shape was. Right, here was our shape. Hopefully this made you think of polars, which is what I did here. Can you see what I did? That's 4 minus, right, factor out. That's 4 minus r squared. And then this is, right, r cosine theta cubed and r sine theta cubed. Factor out the r cubed. Since I was going into polars, I transformed dA into r dr d theta. And I'm not going to do this integration. This is a little this is algebraically kind of heinous. But notice my limits of integration. Can you see what I did here? R equals 0. That comes from a radius of 4. And r equals 2. And then, of course, theta goes all the way around, right? Okay, and I get a very nice number, 8 pi. So I'm going to do this same problem with an alternative formula. Okay, the alternative version of the flux formula. Formula number 2. And I suggest using this on your homework problems number 23 and 25. And these are going to take you a while. There is a lot of hairy algebra in these problems. Okay. This formula, I do need the positive orientation for this alternative version, but it should look a little bit familiar. It has been proven that I can deal with this ds, kind of wrap the normal into it, and do the double integral of what kind of sort of looks greenish. Of course, this means that you have to be able to identify a P, Q, and R component of your vector field, which I have. So example 1 again. This time I am going to call but remember, R is Z in terms of X and Y. So same exact shape. So here's P, Q, and R. R is Z, but remember Z is 4 in terms of X and Y, X squared, Y squared. So this is P dot P times and that's R. Don't forget you have a negative here and here. So that's why I've got negatives there. Simplified stuff up, make sure to replace your your Z. And notice I ended up at the same place. And again, I would have thought polars. And I get the same integrand with the same result, of course. Woohoo! That was a whole lot of fun, right? So only 4 problems for homework. Please give yourself time and please don't put it off. Go ahead and try to manage it. Check all along the way with Slater your steps for 20, especially for 23 and 25, right? The algebra is all bit hangs. All right, let's look at this one. Example 2, compute the flux. Solid enclosed by this shape, 1 minus x squared minus y squared, and the plane z equals 0, right? So bounding it again at the bottom. Sorry, didn't mean to flip there. Notice at this time I gave you, right? Kind of obvious to start with P, Q, and R. Again, notice that Z is right there. So that's where I got my Y, my X, and my Z. And I'm going to use version 2 of the flux formula. Cleaning it up. And once again, notice that with the, I see, hopefully you see some circular things happening here. So you're going to take your dA, transform it into R dr d theta. Here's my 1 plus 4. Right? R sine theta, R cosine theta, times one another is my R squared cosine theta sine theta minus R squared. And again, with my shape here, hopefully you can see that R goes from 0 to 1. And going all the way around, my theta goes from 0 to 2 pi. Expect maybe on an assessment that I would just ask you to get to this place, right? I would maybe just ask you to get to, right? Integrate some, yes, but I am much more interested in can you set this up, make your appropriate choices, rather than, telling me that the answer is pi over 2.